So homework, let me just remind you that the homework 4 is due Monday. And for homework 5, it's online now, so if you want to start early, you can. It's like some questions from the handouts that maybe you didn't get to. And then homework 6 is going to be on a new topic, which is induction. So homework 5 is due Friday. And then I just want to remind you that there's office hours after class. Okay? So before getting into induction, I am going to say some things about units and multiplicative inverses and rings. So, and this is related to the extra. So for homework 4, problem 3 is extra credit. I added some bits and then made it extra credit. So let me just say some things about units. So units in rings. Okay. So let me give you the definition. So definition. So we'll let R be a ring, be a commutative ring. So in this class, all rings are going to be commutative. Okay, so again, a ring has two binary operations, a plus and a times, and both of them are commutative in this case. So let R be a commutative ring. An element R in R is a unit if and only if. So all definitions are if and only ifs. So this is a unit. If and only if there exists some s in R such that R times s is equal to 1. Okay? So it's a unit if and only if it has a multiplicative inverse. So R is a unit if it has a multiplicative inverse. Okay. So just a little remark is that if an element has a multiplicative inverse, it's unique. Has a multiplicative inverse. Multiplicative inverse. It is unique. Okay. So let me give you some examples. So examples. Okay. So there's this field. This is the ring of rational numbers. This is the ring of real numbers, and this is the ring of complex numbers. And all three of these rings, every non-zero element is a unit. Okay? And in this one here, the only units are, plus 1 and minus 1. Okay? So these are the things with multiplicative inverses. Okay, so these guys are special. So these are special rings where every non-zero element is a unit, and they have a name. Okay, and I slipped and I said the name because that's what I was thinking of. So when you have rings where all the elements are units, every non-zero element is a unit, it's called a field. So definition. So a field is a ring where every non-zero element is a unit. Okay? That's a field. So these guys here, so Q, the rational numbers, R, the real numbers, and C, the complex numbers, these are fields. Okay, so those are fields. And so that's what those things are. I just want to, I want to prove this fact to you guys here. Okay, so I want to prove this to you, that the only units in Z are plus and minus 1. So to do that, let me just do a quick fact. Okay, so every A, B over Q, with A and B coprime and B greater than 0 has the following property, that A over B is an integer if and only if B is equal to 1. Okay, so first of all, we've talked about this before, but every rational number can be written this way. Okay, it can be written as this thing, where if they have something, remember, if they have something in common, then you can cancel out the common factors. And so if it was a negative number, you could either make the top or bottom negative, right? But we'll just assume that the bottom's not negative, okay, that the top is, and B is not equal to 0. Okay, so B is a subring, or Z is a subring of Q, right? So every integer is a rational number. They're the fractions of the form A over 1, okay? All right, so I'm just going to use that. So now I want to prove to you guys that the only units of Z are plus or minus 1. So let me state that. So a claim. So the only okay, so here's some notation. So we have Z cross. Okay, so in general, for a ring R, R star denotes the group of units. So the group of units. Okay, so this is the units of this, and this is saying that this is the only two elements are plus or minus 1. So when you write plus or minus 1 like this, it's really two things, plus 1 and minus 1. So this is a cheap notation, cheap way of writing the set plus 1 and the set minus 1. Does that make sense? Okay, so let's do the proof. Okay, and to show that two sets are equal, you need to show, so here's one set. This is the set of units. And here's the set plus 1, minus 1. Okay, so here's the proof. Okay, so to show two sets are equal, we need to show that they are both they are both subsets of each other. Okay, does that make sense? So like if we have two sets A and B, and I want to show that A is equal to B, I need to show that A is a subset of B and that B is a subset of A. Okay? So that's a kind of a general fact. And so whenever you show that an equality of sets, there's two parts. There's one part where you show one inclusion, and you have the other part where you show the other inclusion. Does that make sense? Okay, so there's two parts of this proof. So the easy part will be to show here is a subset of Z star. Okay? So we need to show plus 1 to show plus 1 and minus 1 are units. Okay? So in order for them to be units, they need a multiplicative inverse. So what's the multiplicative inverse of 1? 1, right? So 1 times 1 is equal to 1, so 1 is a unit. So it's a member of the set of units. What's the multiplicative inverse of minus 1? Yeah, so minus 1 times minus 1 is equal to 1, so minus 1 is a unit. Okay, so this proves that this set here, so this shows that, and I'm going to write something, this shows that the set 1 minus 1, this is the same thing as the set plus or minus 1, right? That's what we mean by that, is a subset of this. So, okay, so we need to show, so this is the subset symbol. Okay, so we've shown that these guys are units. That's the easy part. Now it remains to show the other way. So let's show the other direction.
Just to stop here for a second.
Yep.
In the homework, it was using slightly different notation for the subset without that bottom line. Are those pretty much?
Yeah, they're the same. They're the same. Same symbol. Same symbol. So sometimes people write subset not equal to, right? So this is like, so this is like, they're the same symbol, right? You can use them interchangeably. So his statement was that sometimes we use this symbol, and sometimes we use this symbol for subset. So these are the same. They mean the same thing. Sometimes people use this because they like to use a cross through that to say it's a subset, but it's not equal to the same thing. So, yeah. But they're both the same thing. So to do the second part of the proof, right, we need to show this. Every unit is plus or minus 1. OK, so let's find out which elements are units. So without loss of generality, so let me just make a remark here. I'm going to say that we'll be able to work with the positive integers. OK, so suppose n is a unit. By definition, this means there exists some m in z such that nm is equal to 1. OK? I claim that minus n is also a unit, right? If n is a unit, minus n is a unit. So let me just write that what that is. So minus n times minus m, well, this is equal to 1 as well. OK? So without loss of generality, we can assume n is greater than or equal to 0. So we can assume n is greater than or equal to 0 without loss of generality. OK, so that's what. So now I can assume that n is greater than or equal to 0. OK, and since we don't want to deal with. So I really want to show that there's nothing other than 1 and minus 1. OK, so let's suppose n is greater than 1. OK, so here the point is that I'm trying to show that these guys aren't units. So the multiplicative inverse of n in Q is 1 over n. Right? Do you guys agree with that? That's what the multiplicative inverse is. And 1 over n, from the fact we stated, is an element of z if and only if n is equal to 1. Right? When it's written in that form. Right? It could be minus 1, but we're assuming that this is going to be positive. OK? So n isn't a unit. if n is greater than 1, and and hence the only units are plus or minus 1. Okay, so we're done. Does that make sense? So I'm just using the fact that, so what have we done? Okay, we've just done this, so we've just kind of made rigorous the obvious fact that like a half is not an integer, right? And a third is not an integer, so on and so forth. That's all I did. Okay, does that make sense? Okay. So let me just say a little bit about what I'm having you guys do in the homework. So, so on the homework for the next part, on the homework in the next homework, in homework 5, we're going to show that that if f is a field, implies f is an integral domain. Okay, so this is one of these rings where everything has a multiplicative inverse. This is like the rational numbers, the real numbers, the complex numbers. And this is saying that an integral domain is the condition that we gave in the first problem of this homework, right? This current homework, where it says if you have two numbers that multiply to 0, then one of them has to be 0. And this is the thing that you guys have been using all the time in calculus and your other classes. Okay?
Not the second part, correct? The CA equals CB.
They're equivalent. They're logically equivalent. So either one of those things makes your ring an integral domain, right? And we prove in the homework that those two conditions are equivalent. But also there's this stronger condition of being a field. The stronger condition of being a field says that there's multiplicative inverses. The basic idea of this proof is that if you have x times y is equal to 0, you can multiply both sides of that equation by the multiplicative inverse, right? And then you have that y is equal to something times 0, which is 0, right? And that's how you can conclude that integral domain property. That's the idea. Okay? Any questions on this unit stuff? Okay, so that's what units are. Also, I think maybe in the extra credit part, I ask you to show that this is a subset, but for any ring, this is a group. It's a commutative group, right? And here, the group multiplication is the ring multiplication. So notice that this is a group. What's the identity of this group? 1, right? And so what's the group inverse of minus 1? What do I multiply by minus 1 to get the identity? Minus 1, right? It's right here, right? So this is a group, right? So this is a group where the multiplication is a very familiar multiplication. It's not something exotic. Okay. Okay, so now I'm going to start a new topic. The new topic is mathematical induction. Okay, so the idea is, so given a formula, right? Or a proposition about the real numbers, or not about the real numbers, about the natural numbers, n an element of n, mathematical induction, so I'll just say induction, is a tool for proving such things. Okay, so so the idea is right. So let me give you example statements about the natural numbers, right? Okay, so here's a first example statement, right? So for every natural number, n is either even or n is odd. Okay, so this is something that we've said before. So this is something that we could prove by induction. And remember that I said that this was I gave this to you as a fact before to use. So I used this earlier in a class because I didn't prove this thing. Okay, we're now at a stage, once we have induction, that we could prove something like this. Okay, 2. So here's something. So for every n in the natural numbers, right? Well, the derivative, the nth derivative of 1 over 1 minus x looks like n factorial over 1 minus x to the n, n plus 1, like this. OK, so this formula just involves the only free variable, if I get rid of this, right? The bound variable in this formula is n. OK? So, so here, you know, this is something where I could plug in a particular n, like n is equal to 1, and you can see that this formula either holds or it doesn't hold. Okay? So the strategy, so the shape of these statements are, so let me just say what the general strategy is. So okay, so there's 2 steps, right? So show first a base case. So this is like a baby step. So in the case n is equal to 1, right? And then the next thing is to show, so to prove an inductive, show the inductive step. Okay, and to do this, right? Okay, so we assume, so how did I phrase this? So yeah, so assuming, so show how to get to the next case, from one case to the next case in a general way. Okay, so let me just kind of draw a cartoon of what's going on. So all of these things here, so we have like, we're wanting to prove a statement of the form for all n in the natural numbers, p of n. Okay, and so here's a cartoon. So I'm going to draw the natural numbers here. Okay. And then I'll draw this, one more copy here. Okay, so the base case is this thing. So it's like we have this thing here. So this is like p of 1. Okay? And then the inductive step, okay? So here, we'll this part here, this is we'll have p, k, and this will be given, right? And so once this is given, this is like a picture here. So this is one copy of the natural numbers. We want to be able to go to the next step to conclude this thing. So we want to go from pk to pk plus 1. So the proposition about k. So it's like a procedure so that when we have this one, we know how to fill out the next thing. Okay? So if we have this and we have this, notice that I can just kind of like fill out this whole thing, right? So if I know this one, and I know that this one gives me the next one, I just fill out this whole thing, and that makes it true for all of them. Do you guys get that? OK, so that's the idea behind it. In practice, this is what it looks like. So let me show you how it looks in this example. So here's the claim, right? So for all n in the natural numbers, one over 1 minus x, this is equal to n factorial over 1 minus x to the n plus 1. So let's prove this thing. OK, so this is a proof. OK, so we will prove this statement. This by induction. OK, so here, P of n is equal to the statement. So notice that P of n here, this is a mathematical formula. This is a predicate, right? And it returns true or false. And the statement here is that the nth derivative here of 1 over 1 minus x, so this is what this proposition is equal to that formula that we gave. 1 minus x to the n plus 1, like so. OK? So here, P of n is this thing. So this is a true or false statement. It's not like P of n is not this. It's not this. It's this equality. OK? It's a formula. OK? And it has a free variable involving n. OK? So we prove this by induction. We have this thing. So the base case, this proof involves really two proofs, right? The base case, P of 1, right? So we're going to start with P of 1, and we're going to show that P of 1 is true. So d dx of 1 over 1 minus x, so this is equal to, well, this is a power rule. So this is really 1 minus x to the negative 1. So this is negative 1, so I bring it down, 1 minus x to the negative 1 minus 1, which is minus 2, and then we have to do a chain rule, which is minus 1 there, which is equal to, let me just write it up here. Which is equal to, these two things cancel, 1 minus x to the negative 2. OK? So this is one side of it. Also, this thing, n factorial over 1 minus x to the n plus 1, in the case n plus 1, in the case n equals 1 is the following, right? It's 1 factorial over 1 minus x to the 1 plus 1, which is really 1 over 1 minus x squared, right? So this proves P of 1 since they're equal. OK? So does that make sense how I proved P of 1 here? I just checked the formula here. I checked this thing. So I checked this, and I checked that, and I showed that they were equal. OK, notice here that I'm using words too, right? So what people will tend to do is they'll just kind of like plug in 1, and they'll get like 1 is equal to 1, and it's unclear what they're doing sometimes. So try and make it as clear as possible what you proved and what you're doing exactly. OK, so it's like here, I took this formula and I plugged in. I'm saying that I'm plugging in n is equal to 1. So it's easy to see. OK, and so now we'll do the inductive step. OK, so the inductive step is we do pk implies pk plus 1. OK, so we assume that we're at, we're given this, so we assume pk, and we show So yeah, let me just keep it like that. We assume pk, and we'll show pk plus 1. So this almost feels like cheating sometimes, because what I'm going to do is I get to apply the formula that we're trying to prove. So I'm going to get to use this formula, but I need to make sure that the formula allows me to get to the next case. Okay, so let me show you what I mean. So in order to prove pk plus 1, this is what we want to show. What we do is, well, I'm just going to start doing the computation, right? K plus 1 of 1 over 1 minus x, like so. Okay, so that's the left-hand side of pk plus 1. That's when I plug in k plus 1 into this thing. Okay, and let's observe that this is equal to d dx times d dx to the k. And then we have 1 over 1 minus x. Okay, so what does this statement pk say? Pk says at level k, I know that this formula is true, right? So I can use the inductive hypothesis that this formula holds when n is equal to k. So you're going to use it, this formula holds for n is equal to k. So this is the part that kind of looks like I'm cheating, but I get to use it because I'm assuming pk, because that's part of this inductive strategy, right? So this part here is applying the inductive hypothesis. So this is k factorial over 1 minus x to the k plus 1. I have applied the inductive hypothesis that gives me that this thing is equal to this thing in the case that n is equal to k. Does that make sense? OK, so now all it remains to do is let's take the derivative of this. So we can take the derivative of this. Let's do it, right? So the derivative of this, well, we just have a k factorial out front because it's a constant. And then we have a negative, so we use the power rule again. So this is minus k minus 1. Then we have 1 minus x to the minus k minus 1 minus 1. Right? So I brought the power down. So this is really a negative exponent. And then I subtracted 1. And then I have to use the chain rule. So this is the chain rule gives us another minus 1. OK? So this thing here, OK, so this thing here is equal to, well, the minuses here and here cancel. So this is k plus 1 times k factorial times x minus 1 to the, well, minus k minus 1 minus 1. OK, so this thing looks like, well, by the definition of factorial, this is just k plus 1 factorial. The factorial is just, you multiply all the numbers out that are less than that. So we have the first one and then all the lower ones given by this thing. And then we have x minus thing. This is to the k plus 1 plus 1. OK? And this formula looks exactly like the right-hand side here when I plug in k plus 1 for n. Does that make sense? So we have shown, so we are done. Right? We've proved the inductive step here. Right? We've proved the base case. So we're done with the inductive step. Let me just write it out a little bit cleaner. OK? And so since we proved the base case, and the inductive step, we are done. We are donezo. All right? So that's how a proof by induction works. Any questions? OK, let me just remark that sometimes here, people use instead of going k to k plus 1, it just means that you just have to go to the next step. So some people prefer to go from k minus 1 to k. Right? So they'll assume the case at k minus 1, and then they'll go to k. Or they'll use a different letter. They'll say n minus 1 to n. Right? So it doesn't really, we shouldn't really be bothered by that. OK? Another thing, well, that's it. So let's do some exercises, and then I will see what we do here. Okay, so you guys have the induction worksheet? So let's just do, so the exercises, we'll do the induction worksheet. So exercises. So handout 3. We're just going to do handout 3, the whole thing, right? All right. And then I'm going to come around and help you guys.